Okay, now let's discuss the kernel types, right? So we will start with the polynomial kernel. And in order to understand the polynomial kernel, we just said an example here, right? We explained an example here. And this is the same example. This is the same formula for the polynomial kernel, right? Here we have xi, xj, and here we have p instead of 1, right? And instead of p, we are just saying here d. It's the same, right? D is a degree of polynomial, so 1, 2, 3, and p is a free parameter trading off the influence of higher order terms versus lower order terms, right? So this p, if it's 0, then we care about the higher order terms more, right? If it's 1, then we care about the lower order terms. If it's 2, then we care about the lower order terms more and more, right? Now, in order to understand the polynomial kernel better, and honestly to understand the kernel itself better, let's look at this video, this YouTube video. So if we click here, if we go here, you will see SVM with a polynomial kernel visualization, right? And I will leave you the link in the resources. So as you can see here, the blue red dots are not linearly separable. So as you can see here, we have red points and we have blue points, right? The blue points are within the circle and the red points are outside the circle. So we want to separate the red points from the blue points. So they are not linearly separable. So how we can solve this problem? We use a polynomial kernel. So x squared plus y squared, for example, right? So that they can be linearly separated in the 3D space. So as we can see here, what we are doing here is that this is the lower dimensional space. This is the input space. We have the blue points, as you can see here, and we have the red points, as you can see outside the circle, right? Outside the blue points, right? So this is the input space. This is what you have originally. So what will happen right here is that we will transform this input space or transform this data from the lower dimensional space, from the 2D to 3D, right? So as you can see, when we transform each point in the second dimension, right, in the 2D into 3D, what will happen is something like this, right? So right now you have the 3D and we can separate the data better here. So if we go to the 3 dimensions, right, you will see now that the blue points, right, the blue points are here, right, and the red points are here, 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 and here. So how we can separate the blue points from the red points? We can separate them using a hyperplane just like this, right? So if we use a hyperplane just like this, now we separated the blue points. As you can see, the blue points are here and the red points are here. So now focus. What happened is that when we use this hyperplane and we see this cross section, you can see it's actually a circle. So if we map this data again from the 3 dimensions into the 2 dimensions, into the input space, what will happen is that it will be a circle, right? So what you are seeing is that we have a circle that separates the blue points from the red points. But what actually happens is that we transform the data using the polynomial kernel, and after transforming this data, we just separate the data using a linear separator in the higher dimensional space, just like here, right? This is a linear separator in the higher dimensional space. But when we transform the data back, or we do the inverse transformation, right, you see it as a non-linear separator. You see it as a circle. So this is basically the polynomial kernel, or in general, what happens when we use the kernel with the SVM, right? So going back again, this is the visualization for the polynomial kernel. And let's take an example. Let's say, what if the phi xi degree is really big, right? So let's say we have a 16 by 16 image, okay? So we have a 16 by 16 pixel image, right? So this is a very small image, by the way. It's not like a very big image or a medium image even. It's a very, very small image, right? It's a 16 by 16 pixel image. And you apply polynomial, right? Apply a polynomial kernel with a degree of 5. If you do the calculation, right? If you do the calculation, you will see that we have how many features. If we didn't use the kernel trick, we will have 10 power 10 features, right? So if we have 16 by 16 pixel image and we apply a polynomial kernel with a degree of 5, right, and do the kernel without the kernel trick, right, and we do the kernel just like this, right, so we apply the kernel here and we apply the kernel here and then we do the dot product, right? If we do it like this, then we are going to have 10 power 10 features. It's impossible to do so, right? So we need the kernel trick. Using the kernel trick, we are not actually transforming the data, right? We are not transforming the data into the higher dimensional space. We are just calculating what will be the value, the output value or the final value if we did so, right? So this is the trick. Now we have another kernel. So we explained what is a polynomial kernel. Now let's understand the Gaussian radial basis function kernel, or Gaussian RBF kernel for short, right? And this is another technique to tackle nonlinear problems in order to add features computed using a similarity function. So here the polynomial features we are getting, right, they are not actually coming using any intelligence, right? We are not really doing any intelligence, or we don't really have any intelligence in these kernels, right? There is no correlation between the features we are having, right? But using the radial basis function, the features that we get or the features we add in the new space are actually computed using a similarity function. Okay, now if you check this video, and it's also a very, very cool video in order to explain what is happening inside the radial basis function, right? So as you can see here, we have these are data points. So can we separate the data points as they are right now? So can we separate the red from the blue points? No, we cannot, really. We cannot. We need to have something very, very complicated in order to separate the blue from the red. So we are going to use the radial basis function. So this is, as we said, the radial basis function. Before the radial basis function, we have Gaussian radial basis function. And why we are calling it Gaussian radial basis function? Because as you can see, it's taking the Gaussian shape, right? The bell curve shape, right? We have here a Gaussian, and we have another Gaussian, and we have another Gaussian, right? So let's take a look at how we can separate the data points using the radial basis function, right? So we have little mountains, right? These are the Gaussians we built, right? So as you can see here, these two data points are here, and then these two data points are here, and then these are here. So basically we project the data points. Let's say that we have one dimension, right? We project the data points into a two-dimensional space, right? So we have a two-dimensional space or more, right? And we project the data point into this new space. And this new space, as you can see, it's computed using the similarity, a similarity function. Okay, so as you can see now, the data points are very, very separable, right? So here we can just have a linear separator just like this, and now we separated the blue points from the red points, right? Just a line that will cut them, and that's it, right? So going back, you will see that this is how we separate the data points, and this is basically how the RBF works. If you want to know more, or if you want to know more details about the radial basis function, right, or the formulas and so on, you can check this video. It's also pretty cool. So going back, this is the equation for the similarity function we use, right? The similarity function measures how much each instance resembles a particular landmark, right? So what is a landmark? The landmark is basically a point that you choose, maybe randomly or based on something, and we call this point the landmark, right? And we will calculate the similarity between each point, right, and this landmark. So the landmark is basically the reference for this data points, right? So it will be the reference for these data points, right? So as you can see here, the function is between. It's not xi and xj, no, it's xi and l, right? It's exponential, and as you can see here, exponential gamma xi minus xl, right? So this is the distance between xi and xl. We multiply this by gamma, and this is also a very important hyperparameter. And in order to calculate the similarity function or the kernel, we have e power all this, right? And L is the landmark. Now let's talk about gamma. Gamma is basically a hyperparameter that controls the distance of influence of each single training point. So what does this mean? Let's look at gamma, right? Let's have a specific, let's say that L is 0. So basically e power gamma x, right? So let's see if gamma is 0.5, if gamma is 1, and if gamma is 0, right? So if you check the bell curve we saw before using gamma equal 3, you will see that we have a very narrow bell curve, right? Something like this, exactly like this, right? So here, as we can see, and here we have gamma equal 1, and here we have gamma equal 0.5. Okay, so low values of gamma, so if we have 0.5, indicates a large similarity radius. So as we can see, a large similarity radius. So this will result in more points being grouped together, right? Because if we use a gamma like this, right, if we have a bell curve and this bell curve is very wide, then all the data points or most of the data points will be within this bell curve, right? Will be within 10% of the bell curve, for example, right? Now, if we increase the gamma, right, it will be narrower and narrower. So the data points need to be very close to each other in order to be considered in the same class or group, right? So if we have models with very large values of gamma, then these models will tend to overfit, right? Because they need to be very close to each other in order to be considered in the same group. Now, if we decrease gamma, then points that are not really related to each other, right, will be grouped together, or they will be within the same group. So this is also an indicator of underfitting, right? So this is very similar to the effect of the C hyperparameter, right? But it was the other way around, right? Now, this is basically the idea of gamma hyperparameter. And indeed, there is a trade-off between gamma and C. But you need to understand that C is a general hyperparameter for all the kernel types for SVM, right? So if we are using a polynomial kernel, we have C. If we're using Gaussian radial basis function kernel, we have C. If we are using any other type of kernel, we have the C hyperparameter. But gamma is a hyperparameter only for the radial basis function. So let's now understand the difference between gamma and C, or the trade-off between them. So this is the same data set, but using 4 combinations of gamma and C. So as we can see here, if we decrease gamma and decrease C, right? So let's just fix C for now, right? And increase gamma. So what happens is that the model will start to overfit a little bit, right? The model will start to overfit. From 0.1 to 5, the model started to overfit, but it's actually starting fitting the data. It's not really overfitting that much. It's tending to overfitting. So if we increase gamma to, let's say, 20, then we will see a clear effect of overfitting, okay? But if we check this figure and this figure, right, so we fix gamma, right, and we increase C, right, so we have the same gamma and a different C. What you are seeing right now is that the model will also start to overfitting. Right now, if we increase gamma and increase C sharply, you will see that the model is actually overfitting. Now, this is a clear sign of overfitting, because this is not actually the distribution of the data. The actual distribution of the data is something like this, right? So this is the best combination of these two hyperparameters. So you cannot really change gamma without changing C. You need to change them together in order to find the best combination, because the effect of gamma and C are related to each other, right? So this is a summary of what I have just said. Basically, smaller gamma values make the bell curve wider, right? So if we have smaller gamma values, this will make the bell curve wider. So instances will have a larger range of influence. So the decision boundary ends up smoother, right? So if we increase gamma, as you can see, increasing gamma here or here, the decision boundary itself is now smoother than before, right? So as you can see, smaller values of gamma here or here, we have a very, very smooth decision boundary, right? Here it's a very smooth decision boundary, and here also. Here the decision boundary is not that smooth, right? So this is basically the trade-off between C and gamma. And we also have something called the sigmoid kernel, and this is the equation for the sigmoid kernel. It's not that important, but basically you need to understand that the neural networks use this kernel, uses this function as the activation function, one of the main activation functions used in neural networks. And an SVM with a sigmoid kernel is equivalent to a two-layer perceptron. So if you know neural networks, then you will basically understand that two-layer perceptron is equivalent to an SVM with a sigmoid kernel. It's not that important, but it's something to keep in mind. And we have also another kernel called cosine similarity kernel, and this is the equation for the cosine similarity kernel, and it's a popular choice of measuring similarity of text documents, and it's using the L2 norm, right, which projects vectors onto the unit sphere, and the dot product of the cosine is the angle between the vectors. This is not important at all. What you just need to understand is this: if you are using, or if you are working on a project, a machine learning project, and you want to measure the similarity between text documents, right? If you are working, for example, on sentiment analysis and you use SVM, then cosine similarity is the best kernel that you can choose, right? And we have many other kernels that you can choose. We have a kernel called chi-square, we have string, tree, graph, wavelet, and many more, right? You can write your own kernel. Kernel is basically a function, so you can write your own function and say that this is the kernel that you are going to choose. Okay, now that's everything you need to know about the kernel trick, the kernel types, and all this. Now, in order to understand the SVM better and discuss the effects of the hyperparameters and see the effect of the kernel itself, we will start with SVM with linear dataset in the next lesson. So in the next lesson, we will start coding, enough theoretical part for now, and we will understand all this in code. So let's go to the next lesson and see how we can implement all this.